Hello, welcome to another problem session. Today we are going to talk about a very standard problem from forces chapter, and this problem is called conical pendulum problem. Conical pendulum problem. So what's the conical pendulum? It's a regular pendulum where you hang with a massless string. So this is one of the assumptions we make, and has a bob of mass m, which is given to be 0.4 kilogram, 0.4 kilogram, and you swing it so it goes in a circle. So this is circle, but speed is constant, and this speed is given to be 3.5. But length is also given to be 1.2 meter. Okay, we will use these numbers at the end, and these are the questions we are supposed to answer. First we notice right away that tangential acceleration is really easy to answer. If you know the definition of tangential acceleration, the definition is what's the acceleration in that direction? This is called tangential acceleration, and it will depend on speed v. So this is actually if the v was changing, but if v is constant, so this is 0 here, since v is constant. So we can right away answer that one. So the rest of them is about motion in a circle, and let's see what the Newton's laws tell us. Okay, let me draw some free body forces. One of the forces, imagine three-dimensional. Imagine this is xy plane. So this is xy plane, and imagine this is the x-axis. This is the direction of the x-axis. So we pick a time where this thing is the x-axis. So we pick t, so that Bob is at x-axis. It's kind of arbitrary, so it's for simplicity, you just pick it like that. So this will be in the negative z-axis, y will be that way, and negative z-axis, and this is where the mg will be pointed. Tension will be pointed in the actually xz plane. So tension will be pointed in xz plane. So all the calculation will be in xz plane. Okay. Now centripetal acceleration is pointed this way towards the center, because the circle is in xy, and so towards negative x-axis, and magnitude is v square over this radius of the circle. And in this triangle, right angle triangle, from there is r is L sine theta. So this is the opposite of this angle. So these are two forces, and the two forces together causing acceleration in that direction. Of course, there's no acceleration perpendicular to that. They're kind of consistent, right? Because the forces are in xz plane. This would have been y-axis in this picture. There will be no acceleration in the y-axis because there's no force component along the y-axis. So this is consistent. Okay, now we write down equation in the x direction. So this is F equals ma. And we can just work on xz plane. Because we don't need to work on y. So we'll have some component in the x direction. So if this guy has nothing along the x direction, this tension has negative x component. This is theta. So this is 90 minus theta. So cosine 90 will be sine theta. So minus t sine theta is equal to minus m v square over r v square over L sine theta. So we got one equation. Of course, this minus cancel out, and in the z direction we don't have mg is minus mg. The tension, this is the theta, so t cosine theta plus t cosine theta. Okay, so we already answered this centripetal acceleration. So these are two things remain here, and from there we can actually figure out what the tension is and what theta has to be. So let's see, this one, let's write down t cosine theta equals mg and take a ratio of these two that kills t, so we get a tangent theta. M cancels out, and so you have a v square over g L sine theta, and I need to solve this for theta. So if you how do you solve such equation for theta? You bring on this other side, it is sine square theta over cosine theta equals to v square over gl, and you can see that I can bring this on the other side. So let's call this guy something b for simplicity. So I have a sine square theta equals b cosine theta. Of course, I can write everything in cosine, so this will be 1 minus cosine square theta because b cosine theta. Bring everything, it becomes quadratic equation in. So now if I use x equals to cosine theta, we have equation in x is x square plus bx minus 1 equal to 0. So x equals to 1 over 2 minus b plus minus square root of b square plus 4. Now b is known, we can put a number here, it's 3.5 square. G is, say, call it 10. G equals to 10 meter per second square, and L is 1.2. So you can get b here, you can put b inside here and take the positive root because x is cosine theta and all these angles are less than 90 degrees. So we expect x to be positive. So take the positive root, half minus b plus the square root of b square plus 4. And so arc cosine of this will be the angle. So arc cosine inverse, let this be called C, will be C. So you have to find out what the C is by plugging in. So that's the theta, and since cosine theta is C, and now since I know cosine theta, we can just use this to get the tension. So the tension will be, that will means tension is equal to mg over cosine theta, and this is the C, and that's the C. We're going to use mg over C. So I'll leave the numerical part for you to complete. Just to recap, when you read this problem, it seemed like pretty complicated because the motion is in 3 dimensions. But when you look at this 3 dimension, actually the motion is happening in a plane. And once you recognize that plane, I often find that picking a time so that the object is along one of the axes simplifies considerably. So if I pick this object and I chose my x-axis in that direction, this is very critical in terms of simplifying this problem. I didn't have to resort to some vague notion of this way or that way. I just could lay out the coordinate axis appropriately, and situation will simplify. And this also led us to this confirmation that this has to be 0, because if the force is going to be in xz plane, how can there be an acceleration perpendicular to the plane? You know, so this is this important step for us. Okay, this video, the question video came from this website, which I maintain. Also, if you like this video and things like that, please click the like button and things like that. So, or make comments if you have some questions about this. I will probably come to it and reply to your questions. Well, see you in another video. Bye.